Chapter 2: Biosensors: Detecting Disease at the Nanoscale. Biosensors represent a critical intersection of nanoelectronics and healthcare, offering the promise of early disease detection, personalized medicine, and real time monitoring of biological processes. In this chapter, we delve into the principles of biosensing at the nanoscale, explore the role of nanomaterials in enhancing sensor performance, examine applications of nanoelectronic biosensors in disease detection, and discuss challenges and opportunities in this rapidly evolving field. Imagine being able to diagnose disease long before any symptoms appear. Picture a world where early detection becomes the norm, not the exception. This is the promise of biosensors, a remarkable innovation at the intersection of biology and nanoelectronics. In the vast landscape of healthcare, early detection is often the key to successful treatment. Biosensors are poised to revolutionize this aspect of medical diagnostics. These tiny devices can detect biological molecules at incredibly low concentrations, offering a glimpse into the molecular mechanisms of diseases. Biosensors are revolutionary devices that have transformed landscape of healthcare diagnostics. They are powerful tools capable of detecting biological substances, such as proteins, nucleic acids, and biomolecules, that indicate the presence of a disease or infection. Biosensors operate on the principle that when a biological substance binds to a specific receptor or probe on the sensor's surface, it generates a detectable signal, usually in the form of electrical, optical, or electrochemical changes. These devices can be engineered to be highly sensitive, allowing them to detect even trace amounts of target substance. A typical biosensor consists of three main components. Bioreceptor. This is the part of the biosensor that interacts with the target biological substance. It can be an enzyme, antibody, nucleic acid, or other biomolecule that binds specifically to the target. Second is transducer. The transducer converts the binding event into a measurable signal. It can be optical, that is light based, electrochemical, that is electric current based, piezoelectric, pressure based, or thermal, heat based, depending on the type of the biosensor. Third is detector. The detector measures the signal produced by the transducer and translates it into a readable output, such as a digital reading or visual signal. There are various types of biosensors. Let's discuss optical biosensor. Imagine a device that uses light to detect changes at the molecular level. These sensors offer high sensitivity and specificity. Surface plasmon resonance, that is SPR biosensors, for instance, detect changes in refractive index when a target molecule binds, allowing for real time and label free detection of biomolecular interactions. Electrochemical biosensors. Picture a tiny device that can monitor your blood sugar level in real time, alerting you instantly if they go too high or too low. These sensors detect changes in electrical current or potential due to binding events and are widely used for glucose monitoring in diabetic patients. Another one is piezoelectric biosensors. Imagine a sensor that can weigh the mass of a virus particle binding to its surface. These sensors detect the changes in mass on a sensor surface by converting strain due to mass into electrical signal and are used for detecting viruses and bacteria. Thermal biosensors. Think of a device that measures the heat generated due to a biochemical reaction. These sensors detect changes in heat due to binding events and are used in applications like DNA hybridization detection. There are multiple types of biosensors. Let us start with the optical biosensor. Imagine a device that uses light to detect changes at the molecular level. These sensors offer high sensitivity and specificity. Surface plasmon resonance, that is SPR biosensors, for instance, detect changes in refractive index when a target molecule binds, allowing for real time and label free detection of biomolecular interactions. Next is electrochemical biosensors. Picture a tiny device that can monitor your blood sugar levels in real time, alerting you instantly if they go too high or too low. These sensors detect changes in electrical current or potential due to binding events and are widely used for glucose monitoring in diabetic patients. Next is piezoelectric biosensors. Imagine a sensor that can weigh the mass of a virus particle binding to its surface. These sensors detect changes in mass on a sensor surface by converting strain due to mass into electrical signal and are used for detecting viruses and bacteria. Another one is thermal biosensors. Think of a device that measures the heat generated due to biochemical reaction. These sensors detect changes in heat due to binding events and are used in applications like DNA hybridization detection. Let us now discuss applications of biosensors in healthcare. Consider the case of glucose monitoring for diabetes. Traditional methods require frequent blood sampling and can be cumbersome for patients. Now, imagine a tiny implantable biosensor that continuously monitors glucose levels and transmits the data to a wearable device. This real time monitoring not only enhances patient comfort but also provides critical data to manage the condition more effectively. Another remarkable application of biosensors is in the early detection of cancer. Tumor markers, specific proteins, or DNA sequences associated with cancer can be detected at very low levels using biosensors. This enables early diagnosis, which is often crucial for successful treatment. For example, prostate specific antigen, that is PSA levels, can be monitored to detect prostate cancer at its nascent stage. The versatility of biosensors extends to detecting pathogens as well. Rapid and accurate detection of viruses, bacteria, and other microorganisms is vital, especially in the context of outbreaks and pandemics. Biosensors can be designed to identify specific genetic sequences or proteins unique to the pathogen, facilitating timely interventions. Multimodal biosensors are becoming increasingly sophisticated by integrating multiple detection modalities, such as optical and electrochemical methods, into a single platform. This integration aims to enhance both the sensitivity and reliability of biosensors, making them more effective in various applications. Another significant advancements in biosensor technology is the incorporation of advanced nanomaterials, such as graphene and carbon nanotubes. These materials are utilized to improve the performance and functionality of biosensors, offering superior detection capabilities. Additionally, the integration of artificial intelligence into biosensor systems is revolutionizing the field. AI algorithms are used for data analysis and pattern recognition, significantly enhancing the diagnostic accuracy and predictive capabilities of biosensors. This combination of advanced materials and AI is paving the way for more efficient and reliable biosensing technologies. In this chapter, we have explored the transformative potential of nanoelectronic biosensors in detecting diseases at the nanoscale, from cancer diagnostics to infectious disease surveillance. Nanoelectronic biosensors offer a powerful tool for early detection, personalized treatment, and improved patient outcomes. As research in this field continues to advance, The promise of nanoelectronic biosensors in revolutionizing healthcare remains brighter than ever.